back to this part of the video where we're going to talk about shifting and rescaling the data. When we standardize data to get a z-score, we basically do two things. The first thing is that we shift the data by subtracting the mean. If you'll recall, the formula for z-scores is value minus mean divided by standard deviation. So the next thing is, when we divide by the standard deviation, we're actually rescaling the data by dividing by the standard deviation. It's not unusual to shift and rescale data, okay? So we need to think about, like, if we had a grade distribution, for example, let's say everyone gets a 5-point bonus. What would happen to the average? Or if we switched from feet to meters, what happens to the distribution of heights of students? We're going to investigate what happens there when we want to shift maybe from seconds to minutes, in other words, okay? So please pause the video and read the problem, and then unpause when you're ready to work it out together. The teams in men's combined event at the Winter Olympics are reported in seconds. The mean and standard deviation of the 34 final super combined times at the 2010 Olympics were 168.3 seconds and 2.90 seconds, respectively. Suppose instead that we had reported the times in minutes, that is, that each individual time was divided by 60. What would the resulting mean and standard deviation be? So what do you think would happen if we converted from seconds to minutes? Well, let's find out. First, we need to remember that there's 60 seconds in 1 minute. So I have my mean, which is just 168.3 seconds. And if I want to convert that to minutes, I need to divide by 60 seconds so that the seconds cancel and I'm left with minutes. So 168.3 divided by 60 is 2.81 minutes. And then for the standard deviation, I'm going to do the same thing. It's 2.90 seconds. To convert that to a minute, we're going to divide by 60 seconds. And 2.90 divided by 60 gives us about 0.05 minutes. Okay, please pause the video and read the problem. And in this problem, I want you to reflect on what's happening when you add points or add values to a set of data values. What happens to the mean and what happens to the standard deviation? Okay, and kind of visualize what box plots would look like there and how would they be different and the same. In 1995, the Educational Testing Service, ETS, adjusted the scores of SAT tests. Before ETS recentered the SAT verbal test to 500, the mean of all test scores was 450. So how would adding 50 points to each score affect the mean? So let's investigate that. What I did was I typed into my calculator a set of numbers. I went into stat, and I typed in numbers where in list 1, the average was 450, and in list 2, I added 50 points to each of those original values. So 300 plus 50 is 350, 350 plus 50 is 400, and so on. And what we want to do is pay attention to what happened to the average for that. So to find the summary statistics, remember you go to stat, and then we're going to go to calc. And this time we have two variables we're going to look at. So we're going to hit number 2, okay, because we have 2 columns there, and I want to find the summary statistics for both. So here we go. If we take a look, okay, we can see that the average X bar was 450, and in my second list, Y bar ended up being 500. Now, if you remember, we added 50 points to each of the scores. So how did the mean change? It went up by 50 points, right? It went from 450 to 500. Okay, so if you increase each point by each score by 50 points, the mean is also going to go up by 50 points. Okay, let's say, as we can see here, the standard deviation was 100, right? So that's your sigma x, the population is 100. Even adding 50 points to the each of the test scores, as you can see, sigma y is also 100. So all it did was rescale. It just shifted the data to the right. That's all it did, but the spread stayed the same, okay? So the spread, as you can see, did not change. So adding 50 points to each of my scores, it increased the mean by 50 points, but the standard deviation stayed the same. Why? Because all those points, all those scores did was just shift the same distance. So they're still going to be the same distance apart on average from the mean. Okay, so how would adding 50 points to each score affect the mean? The mean would increase by 50. And the standard deviation would just remain the same. So here, my x bar ended up being 450, whereas here, my y bar for my second set was 450 plus 50, which came out to 500. And then my standard deviation for my first set was 100, and when you add 50, it stayed the same. Okay, it just shifted. All the points just shifted. Try to visualize what a box plot of the test taker scores a year before and a year after the recentering. How would the box plots of the 2 years differ? So they would look nearly identical. The shape would remain the same, right? But the later one would be shifted 50 points higher, okay? So we can probably take a look at that on my graphing calculator. If you remember, we want to just go to second plot, and we want to make sure our plot's turned on, make sure the box plot is highlighted there, okay? And then the same thing with my other plot, and all I have to do is hit zoom 9, and it's kind of hard to see. Let's see if we can change the window. So let's make my X max 1,000, or X min, I'll make that 400. My X max I'll make 1,000. And then my Y min, really we don't need that, but let's see what happens now when we hit zoom 9. Okay, now you can see. So the basically the shape is the same, okay? It's just as spread out as the original one was. It's just that you can see that the later one, the red one, is shifted 50 points higher. So the median, where the vertical bar is for the blue graph, your original data set is at 450, but the mean for the when the 50 points was added is shifted to the right. Okay, but you can still see that the boxes, if you could kind of shift that red one down and put it right under the blue, it would be the same distance apart, right? So the interquartile range, the box, does not change. Okay, so let's kind of summarize here really quickly what we found. Adding or subtracting a constant to every data value, what does that do to the measures of center or position, and what does it do to the spread? Well, remember, as we just saw, it adds or subtracts. So if I was to subtract 50 points from each of the scores, the mean would decrease by 50 points. The same constant, two measures of position, and it leaves the spread unchanged, right? Standard deviation we saw did not change at all, because all it does is shift the data up or down. And you can try this when you multiply or divide all the data values by any constant, all measures of position. So what we mean by that are like the mean, the median, percentiles, things we've talked about, and measures of spread, which are like range, IQR, standard deviation, are multiplied by that same constant. So here we know that when you multiply or divide all data values by any constant, all measures of position and measures of spread are changed, whereas adding only changes measures of position. Standardizing data into z-scores is just shifting them by the mean and then rescaling them by the standard deviation. And then think about, how does standardizing affect the distribution of a variable? Okay, so we have some things to remember here. Standardizing into z-scores does not change the shape, as we saw, okay, with the box plots. It does change the center by making the mean 0, and standardizing into z-scores does change the spread by making the standard deviation 1. Okay, if you could, please pause the video and then unpause it when you're ready to solve this problem. Many colleges and universities require applicants to submit scores on standardized tests such as the SAT Evidence-Based Reading and Writing, which is EBRW, and math tests. The college your little sister wants to apply to says that while there is no minimum score required, the middle 50% of its students have combined SAT scores between 1100 and 1350. You'd feel confident if you knew her score was in college's top 25%. But unfortunately, she took the ACT test, an alternative standardized test. How high does her ACT need to be to make it into the top quarter of equivalent SAT scores? Note, for college-bound seniors nationally, the average combined SAT score is about 1083, and the standard deviation is about 191 points. For the same group, the ACT average is 20.8 with the standard deviation of 4.8. So for this problem, we want to think, show, tell, okay? So let's think about what we're looking for here. What is it that I want to find? I want to know which ACT score corresponds to the upper quartile, or top 25%, right? Or 75th percentile is another way to look at that. SAT score, okay? Because remember, your sister took the ACT. So what I need to do is, since they talk about the middle 50%, right? I know middle 50% is the IQR. So I already know my Q1 would be 1100 and my Q3 would be 1350 because the IQR is Q3 minus Q1. Okay, so this is your middle 50%, which is your IQR. Okay, so what I can do here is find my z-score, okay? And I'm gonna find it for 1350, which is the top 25%. I'm gonna subtract the average for the SAT group, which is 1083, and then I'm going to divide that by the standard deviation, which is 191, and I get 1.40. So what does that mean? It means 1350 is 1.4 standard deviation above the mean of all test takers. Okay, so now I can use that and I can convert it, use it to convert to the ACT score, which would still be the top 25%. So I'm going to take my z-score formula and I'm going to plug in 1.40 for z, And this time I'm trying to look for the cut score. Like, what would be the score on the ACT that would still allow her to be in the top 25%? I'm going to subtract the mean of the ACT score, which is 20.8, and then divide by the standard deviation for the ACT score, which is 4.8. Okay, and then how do I work this out? So to solve for x, I need to multiply both sides by 4.8. And 4.8 times 1.40. 4.8 times 1.4 is 6.72. So you would get 6.72 equals x minus 20.8. And then I'm going to add 20.8 to both sides. And that gives me 27.52. So that is what ACT score corresponds to the top 25% SAT score, okay? So in other words, we could say something like, to be in the top quarter of applicants in terms of combined SAT score, she'd need to have an ACT score of at least 27.52. And that is the end of this video. Please stay tuned for the next part where we talk about the standard normal model and begin to get into the normal model empirical rule. Have a great day, everyone.